Hello. In this video I wanted to give you an introduction into several specific types of forces, and today we're going to talk about weight. Over the course of the next couple lessons we'll learn also about tension, and we'll learn about compressions and spring forces, and we'll learn about friction. I might also create a video on drag eventually, and thrust, and a handful of other interesting forces. But today's lesson, weight. Weight is caused by the gravitational attraction between the Earth and whatever object you're interested in. It is calculated using a formula, W equals mg, and m is the mass of the object, usually in kilograms, and g is the number 9.8, which is something we've used a lot in our kinematics formulas as well. You can also measure the mass in slugs and use the conversion of 32 feet per second squared for g, but most of the time we're thinking in kilograms and newtons. So g varies from place to place, and so if you were to go say to the moon, the gravity on the moon is about a sixth of that here on Earth. And in other planets and so forth, gravity can be more than Earth, or on Jupiter it's significantly more than Earth. Venus and Mars have gravitational constants that are significantly less than Earth. So anyway, it varies from place to place. Even on Earth, it varies a smidgen. If you were to go up on the poles, it's a little bit less than it is at the equator, or up on a mountain. Because you're a little further from the center of the Earth, it's slightly less than down at sea level, but usually not noticeably less. I want to talk a little bit about what's the difference between mass and weight. Aren't they the same? Not quite. The mass of an object is how much matter it has. It really boils down to how many protons and neutrons and electrons make that thing up. You count them all up, and yeah, there's a conversion into kilograms, but that's what mass is just how much stuff you're made out of. It also conveniently is a measure of how how well you are at resisting change. The more massive you are, the less you're going to accelerate if somebody pushes on you or pulls on you with a certain amount of force. That's a consequence of Newton's second law, F equals ma. So an object's mass is relatively constant everywhere. You take an astronaut who weighs has a mass of 65 kilograms on the Earth, and you put him in orbit, he still has a mass of 65 kilograms. You bring him to the moon, he still has a mass of 65 kilograms. That doesn't change wherever you go. Masses are always measured in kilograms or grams, and I suppose if you're using the English system, in slugs. But that is that's what mass is. Weight is a force. It's an amount of push or pull. Specifically, weight is your how much you're pulled downward towards the center of usually the Earth. So I suppose if you went to the moon, then it would be how much downward attraction you are to the moon. And that does depend a little bit on where you are, as I've mentioned a bit. Weights are always measured in newtons or in pounds. So I wanted to just do a couple example calculations to calculate a weight of say 800 grams. If we use the formula W equals mg, the mass is 800 grams, and gravity is 9.8, and the units we're familiar with for that 9.8 from our kinematics formula is in meters per second squared. Another convenient unit to work with is that that 9.8 is the same thing, or that meters per second squared is the same thing as newtons per kilogram. And in this chapter, that's probably the more likely or the more useful unit to have that 9.8 memorized in, because if we ever use it, it's probably to convert between newtons and kilograms in a weight calculation like this. We can't exactly multiply these numbers as is, because grams wouldn't cancel out kilograms, and so I'm going to multiply. Let's make this on top, and let's see, there's 1,000 grams in a kilogram. And so if I multiply all these things together, the 800 times 9.8 divided by 1,000, that gives me 7.84 newtons. So if I need to convert that into pounds, then 7.84 newtons. The conversion factor between newtons and pounds is that there are 4.45 newtons in 1 pound. And so multiplying, or I guess dividing those two numbers, gives us 1.76 pounds. So 800 grams weighs approximately 1.76 pounds. Now, weight is a specific example of a much bigger, broader attractive force, and that is universal gravitation. Any objects that have mass are attracted to any other objects that have mass by gravity. Typically, those attractions are usually too small to notice, but they're there. I have mass, and my computer has mass, and so there's some sort of an attractive force between my computer and me. I can't feel it. It doesn't hover or anything. When I move away, it doesn't follow me or anything like that. It's not strong enough to overcome other forces like friction, but it's there. And we can calculate that by using this law that Newton discovered. The force of gravity between any objects is equal to a constant called g. Sometimes we call this big G. That's capital letter G. It's not the 9.8 number, but a much smaller number. It's 6.673 times 10 to the negative 11th. That's how small that number is. But we multiply that constant by the masses of the objects of interest and divide that by the distance they are away from each other in meters squared. So I thought I probably should demonstrate this by doing a calculation. And so the question is just how much attraction is there between two random students sitting in physics class across the room from each other. So suppose you've had your eye on that girl for some time now. Is there some sort of an attractive force, a measurable amount that you can find? Let's do this. So here's our formula. Force of gravity is equal to G times the masses of you and that special someone. And you divide that by the distance between you guys squared. So let's throw in some numbers. G is 6.67. It's typically enough, but you could throw the 3 in there too. Times, where's my times button? There we go. Times 10 to the negative 11th. And we need some masses. Let's, we'll call you 65, and she's a little smaller than you. Maybe she's 60 kilograms. And let's see, across the room from each other, so maybe 4 meters apart. So now that has to be squared. So when you type all these numbers in, you get 1.6 times 10 to the negative 8th power. And that would be in newtons. So to give you some idea of how big, or really how small that number is, written out, that would be 0.1, 2, 3, 4, 5, 6, 7 zeros, and then the 1.6 newtons. So that's not a whole lot, but it isn't exactly zero either. It reminds me of the Dumb and Dumber quote when he says, so what are the chances of guy like you and a girl like me, you know, getting together sometime? And she says, probably 1 in a million. And of course, the line is, so you're telling me there's a chance? Yeah, I know, I totally botched that quote. But anyway, there's a little bit of an attraction force. But to be honest, you're probably much more attracted to that guy right next to you who's only a half a meter away sitting in that seat. And that's just awkward. So I think I'm going to be done for now. So check back tomorrow for another video, this time on springs.